Hi, today we're going to be looking at Rolle's theorem and the mean value theorem. This is section 6.8 and it's one of 3 items that we haven't quite completed yet in the option topic. We're going to complete these in the next couple of lessons. Basically what we need to do is remember first off the definition of a continuous function. So I've put that right up here. The continuous function on a closed interval, f is on a domain D, defined into the real numbers r, is continuous on the closed interval AB. That means that for all c in the interval AB, just put that right here, all c in AB, the limit as x goes to a from the left-hand side of f of x is the function value not at a but at c. And we should have x going from c because c is the point we're trying to analyze here. So the limit as x goes to c from the right of f of x is f of c, and the same as when it goes to left. So just change those things in blue to make the definition correct. And differentiability means the same thing. We have to change the c here down below. So we're looking at the point it's differentiable at a point c if the left-hand limit of and the right-hand limit. So here's the right-hand limit of f of x minus f of a, where x minus a exists, and if on the left it's the same thing, change all those there in blue, then the right hand limit and the left hand limit of f of x minus f of b over, and we need of course c here, c here, c here, and c here. Okay, so these blues lines are corrections. Okay, having had corrected those definitions, now we can look at Rolle's theorem. Rolle's theorem is pretty straightforward. It says that if a function is continuous on a closed interval AB and it's differentiable on the open interval AB, and we know that f of a and f of b is 0, then there will exist a value c in the interval AB such that the first derivative or of f of at c is 0. In other words, the slope of the tangent at c is 0. Okay, now it doesn't really make a lot of sense in its notational form, but if we look at I'll put proof in quotation marks. This isn't really a proof, it's more of a demonstration. Basically what this says is that the function is on the x-axis at the endpoints of the interval. The endpoints of the interval. If that's the case, then basically the graph is going to start here and here on the x-axis. Now it could be a number of different cases, but if you look at all of these cases here, I'll highlight that the endpoints are always here at 0. Okay, and f of the endpoints is 0. So it could be, for example, that the function just rises up. It's differentiable. And so if it's going to rise up, it has to come back down because it's continuous and differentiable. And that would mean there's some place it has a flat tangent at c. Okay, it could be that the graph went down, but still it has to come back up because it is continuous. Okay, it can't, and differentiable. It can't continue to rise because if it did that, it wouldn't get back down to b. Okay, if that's the case, then at some point along here, there's going to be a first derivative that's equal to 0. Hey, it could have 2 points where the first derivative is equal to 0, such in this third case. Okay, so you've got a first case here at c, and you've got one there. It doesn't say that c is unique, it just says that there is a point c, such that f prime of c is 0. And I guess the degenerate case is that the graph is really just always along the x-axis, in which case all the points in the interval are giving you that f of c is equal to 0. And this is basically Rolle's theorem. The real proof is beyond the scope of the course, but we get a feel of it from these 4 cases. 3 cases, really. Now, the mean value theorem is a little bit different. Actually, this we can prove. It's going to use Rolle's theorem. And again, a little correction to add here. It says, suppose that a function, make this a little a, f mapping from D to R is a continuous on the closed interval AB and differentiable on an open interval, then f of B minus f of A is equal to f prime of C of B minus A. This is weird looking, but it'll make sense in a sec. For some C in AB, and then this part we can just cross right out here. I think I copied and pasted from the note above, and I didn't need to put that in there. Okay, so basically, before we prove it, it's nice to take a look at what this might mean. Okay, so if you take the statement of the theorem and rearrange it, okay, to be something like this, what it's saying is that the slope of the tangent at some point C, that's right here, here's my tangent, and this is the slope, okay, is equal to the slope of the line segment between A, f of A, and B, f of B. That's this red line right here, okay? So the slope here is f prime of C, and of course the slope here is the rise over the run, okay? So the statement of the theorem really just says that at some point, if you take a line between the two endpoints of the interval and you draw a line segment there, at some point there's a tangent line that has the same slope. In other words, it's parallel to that line segment, okay? So there's some point that this line segment here and this line segment here are parallel. Okay, so how do you prove this? Well, basically we set up a function called h of x, okay? Underline that right here, and that's f of x minus this crazy slope of the line segment between the two intervals, the endpoints of the interval, times x minus a minus f of a. Now, if you look at h, a couple of things you'll notice about h. First off, if you plug a into h, okay, we have to replace all the x's with a. We get f of a, and then inside the brackets here, this is a constant. And then we get an a, excuse me, an a for this x here and here. And then the last bit's just a constant, was this f of a. And so if you evaluate this whole thing, you see it ends up just being a 0 here. This is 0. And then we have f of a minus f of a. So there's f of a minus f of a, which is 0. So h of a is 0. And h of b, if you look at that, we get f of b minus f of b minus f of a, b minus a, have b minus a, and then f of a. Now if we look at that, then you can see that we have here and here the same thing, so we can cross those out, and we're left with f of b minus f of b plus f of a. We need to bring this negative sign right there through the brackets, minus f of a, and once again we have 0. So we have a function called h that is 0 on two of the endpoints of the interval AB. And if you notice, since h is nothing more, since h is nothing more than bits and pieces of f and x all added, multiplied, subtracted together, this is two different points here. We have a third point. H is continuous on AB and differentiable on the open interval AB. So this function A fits the conditions of Rolle's theorem, which means that there is some point C. So we do all of this, we can just make a little line here and say, by Rolle's theorem, there is a C in the open interval AB such that h prime of C is 0. Okay, so if we take the derivative of h, we know h prime of c is 0. Now what's the derivative of h? Well, if I can just turn the highlighter on once again, let's change colors here. We've already highlighted the x's. Wherever there's an x, we need to take a derivative. When there's no x, it's a constant, and so the derivative is 0. So h prime of c is 0 really means that we go over here, f prime of x minus this whole crazy coefficient in front of the x is the derivative of that linear term times the x, and all of that's equal to 0. So we end up with that this is equal to 0, and this isn't at x, excuse me. Let me just change that. This is actually evaluated at c. And there you have it. We have the exact condition of the theorem, that f prime of c is equal to the slope of that line segment between the two endpoints of the interval. So if we can just add that in here, we have f prime of c is equal to f of b minus f of a over b minus a. And if we highlight this condition here and this condition here, we can see the same. They are the same. So really, the mean value theorem is just an application of Rolle's theorem.